The second example we'll do will be to work out the electric field due to a line of charge. Now you remember we did this earlier, and we did it as a ring rather than a line to make it easier. Because with the ring, every point on the ring is an equal distance away from the point P. But this is a much easier way to do it when we use Gauss's law. So we can now have a line of charge in a straight line, because we're going to pick our Gaussian surface so that all of the surface that matters is an equal distance away from the line, because the electric field, if the line were to be vertical, the electric field will come out horizontally and it will come radially out from the line, and that means it'll cross all of the curved surface of the cylinder at right angles. So let's go through the working now. Let's start with a line of charge. We'll show it here with some charge on it. And we want to know the electric field a distance r away from that line. So we'll put a Gaussian surface that is the shape of a cylinder. Cylinders are good, they've only got 3 surfaces, each end, and then the curved surface in the middle. And we're going to give our cylinder a radius r and a height h. So we know that the flux coming out from that cylinder will be the flux coming out through each surface added together. The good thing is, if you were to look at this line of charge from one end, you would see that the electric field lines are coming radially outwards. And that means there's no electric field coming through each end of the cylinder. The only part of the cylinder with electric field through it is the curved face. And so we're going to look at each little bit dA of the curved face of the cylinder. So we can say that phi total, which would be the phi at the ends plus phi of the cylindrical face, is just equal to the phi through the cylindrical face. So at the surface of the cylinder, we know that r is a constant distance away. So all of that surface is the distance r. And that means the electric field strength will be a constant all through that surface. The other thing is that E is coming radially outward, so it's at right angles to that surface. So phi is going to be the integral over that curved surface of E dA, which would be E dA cos theta, but cos theta is 1. And E is a constant, so we can pull it outside the integral. And we are just integrating the surface of that cylindrical face. So what would be the area of this surface? If you were to cut the cylinder open it out, you would see it's actually a rectangular shape. And one side would be the circumference of the circle, which is 2 pi r, and the other side would be h. Now, Gauss's law tells us that E naught times the total phi will equal the charge inside the cylinder, the enclosed charge. So we have E naught times that total phi, which is E, 2 pi r h. And now the charge inside the cylinder, we have the charge density, lambda coulombs per meter, and so the charge inside will be the charge density times the length. So we have that equals lambda times h. H's are going to cancel, so we are left with E equals the charge density over 2 pi E0 r. And that is the result for the electric field a distance r away from an infinite line of charge.